This is Calculus 12, Chapter 3.9. We're going to be looking at derivatives of exponential and logarithmic functions. So exponential functions, for those who haven't done it yet, look like powers. However, the major difference is the variable is in the exponent rather than the base. And the base must be a positive constant. So we have y equals a to the power of x. And the domain for exponential functions is all reals. The range for untransformed exponential functions is y is greater than 0. And untransformed exponential functions are always increasing. Now, definition of a logarithm. The logarithm of a number is an exponent. Log base b of c is the power to which b is raised to get c. The base of the logarithm is the same as the base of the power. So when we have log b of c equals to a, this means c equals b to the power of a, where b and c are greater than 0, and b does not equal 1. Exponentials and logarithms are inverses of each other. So this is an exponential, this is a logarithm, and all we're doing is moving the numbers around. So the 4 goes there, 64 goes there, and the 3 goes there. Okay, so the 3 is the power. So logarithm gives you the power. And just a quick refresh of your log laws. And you can go through these examples by yourself, but basically, if we take log a of x plus log a of y, this is log a of x times y. And for division here, we have log a of x minus log a of y. That's the same as log a of x divided by y. And log a of x to the power of k, we can bring the exponent out to the front. So this is k log a of x. And let's just quickly fill in these values. This equals log 2 to the power of 9. This equals log 32. We're just multiplying. Here we have log 3 to the power of 3. Here we have log 4. And we have 4 log 5 to the power of 2. And we have 3 log 6. We also have other log properties. Log a of 1 equals 0. Log a of a equals 1. Log a of a to the power of b equals b. And there's also a change of base. So if we're doing log b of a, there's two formulas. We can do log c of a over log c of b. Or we can simply just do log a over log b. Now, you've been doing exponential functions, but you probably wouldn't have seen e to the x, and it's the most interesting function. We can calculate e to the x as an infinite sum. We start at 0, go to infinity, and each term is represented by x to the power of n over n factorial. So we have this series. Now, if we wanted to just calculate e, we would have e to the power of 1. This would be 1 plus 1 plus 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial. And you can see that this will converge very quickly to e, because these factorials grow very quickly. Another way that e to the x can be represented is by taking the limit as n goes to infinity of this binomial to the power of n. And the last interesting thing that we'll cover is the derivative of e to the x is simply e to the x. And let's look at the proof. And before we start the proof, we need to have a property. If we take the limit as h goes to 0 of e to the h minus 1 over h, this is 1. And another way to look at it is the limit as x approaches 0, e to the x minus e to the 0, x minus 0. Okay, and if we go back, we see e to the power of 0 is 1, and we see that x minus 0 is just x. So this is the same way of looking at it. So we want to define f of x is equal to e to the x. The derivative, we use our normal derivative definition. And we want to take the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's not a difficult step. So let's substitute. Limit h goes to 0. And we substitute x plus h minus e to the x over h. Now we want to factor this. Limit as h goes to 0. We want to factor out e to the x. That leaves us with e to the h minus 1. Okay? If we factor out e to the x, we're left with 1. And over h. Remember, this is what we want, so we need to just get rid of this. So, since there's no h's involved, we can bring this to the outside. But we'll just take the limit anyways. And this is a multiply. Limit, h goes to 0. And we're left with e to the h minus 1 over h. This simply becomes e to the x. Again, h is not involved, so we just evaluate it. Here, we have a big thing. However, it equals this, and this equals 1. So we're multiplying by 1. So our derivative is e to the x. Okay, we're not going to be asked to do the derivative of e to the x because it's too easy. So it's more likely the case that we're going to have e to some function u. That means our derivative is e to the u du dx, or the derivative of u. Okay, let's take a look at an example before we go through the rest of the proofs. On page 3, we have y equals e to the power of negative x over 4. Find the derivative. Y prime, well, the derivative is e to the u. Now we need to multiply this by d dx of the exponent. Negative x over 4. And this is a linear function, so the derivative is just negative 1/4. And if you like, you can rewrite this minus e to the minus x over 4 over 4. So that's derivative of an exponential function using the chain rule. Now we need to find the derivative of a to the x. Not everything's always going to be e to the x. So how do we do this? Well, there's an exponential rule that says this is equivalent to x ln a. And the way we see this is ln x equals log e of x. Since these are inverse functions of each other, this a can simply replace the e. Okay, so the derivative of this is itself, e x ln a. Now we need to take the derivative of the exponent. Now we can substitute this back, a to the x. And the derivative of this, it's just a constant times x, so ln a. And that's our derivative. So it's the same exponential, but we're multiplying it by ln a, the base, ln of the base. And of course, we're not always given easy functions like this. We're going to have to use a chain rule on a to the power of u, where u is a function. So our derivative is a to the u, ln a, and of course we need to take the derivative of u. Okay, let's look at an example before going through more proofs. So y equals 9 to the power of negative x, so y prime equals 9 to the power of negative x. We multiply this by ln 9. And now we need to take the derivative of the exponent, d dx of negative x, and that's just negative 1. So our derivative is negative 9 to the power of negative x times ln 9. Okay, let's continue with the rest of our proofs. The derivative of ln x, and x is greater than 0 because we can't take the ln of negative numbers. We have y equals ln x. Well, this doesn't do us very much good because we're trying to find the derivative. We don't know what the derivative is, so we can't just do this. So one way to solve this is by exponentiating both sides. So we have e to the power of y equals x. E to the power of ln x cancels each other out because they're inverses. Next step, we do implicit differentiation. So we're differentiating every term with respect to x. So d dx e to the y equals d dx of x. So we've already calculated this. This is e to the y. And because we're differentiating with respect to x, we need to use the chain rule. This is y prime. The derivative of this is simply 1. Now we isolate y prime. Y prime equals 1 over e to the y. Okay, and this last step is where people miss what to do. We know what e to the y is because we have it up here. This is from 1. So that's just x. So y prime equals 1 over x. So the derivative of ln x is 1 over x. That's very simple. Maybe not so simple to prove, but it's simple to use. And again, chain rule. We're not always given ln x. We're given ln of some function. So we have 1 over that function. And again, we need to take the derivative of that function with respect to x. So let's see an example. Okay, so we're not taking the derivative of ln first because we look at the outermost function. It's a squared function, so that's a power rule. So y prime equals 2. We take that function, reduce the power by 1, and now we take the derivative of that function. And we can just get rid of that 1. And we have 2 ln x, and the derivative of this is 1 over x, and that's a multiply. And that just simplifies to 2 ln x over x. I see an x, I see an x, don't cancel. This is a parameter, this is an x. Okay? You can't take this x outside of the ln function and cancel it out. Okay, let's look at our last proof. Derivative of log a of x. This proof is not terribly difficult. So we want to take the derivative However, we'll do a change of base. We'll use e as our base, so we'll use ln. So we're taking ln x over ln a. Now, ln a is a constant, so we can factor it out. So this is 1 over ln a. Now we're doing dx of ln x, and that's easy. So we have 1 over ln a times 1 over x. And we want to rewrite this as 1 over x ln a. Okay, so that prevents us from doing 1 over ln ax, where it's ambiguous where the x is, inside the parameter or outside the parameter. And of course, we have the chain rule. So if we're taking log a of u, we simply have 1 over u ln a, and we take the derivative of u with respect to x. Let's look at an example. So y prime equals 1 over, we take u, square root x plus 1, and we're multiplying by ln 10. Now we also need to take the derivative of u, dx, square root x plus 1. You should know that dx of square root x equals 1 over 2 root x. That's a common derivative that we take. So rather than converting it to a power all the time and working with a power, we just go straight to 1 over 2 root x. So we have 1 over square root x plus 1 times ln 10 times 1 over 2 root x plus 1. Now, technically, we're supposed to take the derivative of this, but this is linear and it has a slope of 1, so we don't bother. Now, we have a square root x plus 1 and a square root x plus 1, so we should simplify this. We have a constant, so we'll put that first. This times this gives us just x plus 1. And then we have ln 10. And that's it for this derivative. Let's look at a hard problem. Okay. This looks like it's a power rule. However, this is not constant. We cannot just pull that out and subtract 1. We have to do something else. And from our pre-calc, we know that sometimes we use logs to solve exponential problems and exponentials to solve log problems. And this is one of those cases. So we take the ln of both sides. And if we're taking the ln, this is the exponent, so it comes out front. And we have ln x. So we no longer have an explicit function. That means we need to use implicit differentiation. So ddx of ln y equals ddx of tan x ln x. This is a product, so we must use the product rule. But first, let's deal with this side. This is ln y, so the derivative is 1 over y. And because we're not differentiating with respect to y, we need to use a chain rule, so we have y prime. So, product rule. ddx tan x times ln x plus tan x ddx of ln x. Okay, so now we have y prime over y. We'll just simplify that a bit. Derivative of tangent is secant squared times ln x, tan x, and the derivative of ln x is 1 over x. Okay, now we need to multiply y by the right-hand side. And I'll just put this in brackets and divide it by x, just so I have more space. So y prime equals, well, we can't leave the y here because this is an explicit function. That means y equals something that doesn't contain y. So we shouldn't have y in our derivative. But this is easy. All we need to do is replace y, and y equals this. So x, tan x as the exponent, and then we just copy the rest. And one more bracket. So there's not a lot of arithmetic here. It's just about following rules and looking up derivatives. And as long as you can keep that straight, you can do calculus. So that completes this lesson.